Hello, I'm Dr. Ala Kamerdiner. Welcome to Discrete-event simulation. This is lecture 22, Statistical Analysis of Output from Steady-state Simulations. I will talk about warm-up and run length, truncated replications, batching, and also will discuss other methods and goals. So recall the difference between terminating and steady-state simulations. As you remember, the terminating simulation studied the simulation on a certain time period or some time interval, while steady-state simulation wanted to understand the system as it runs pretty much forever. So, as you remember, deciding which is an appropriate one basically depends on the goal of the study and not so much on the model structure. So we would choose the terminating if we wanted to learn more about the behavior of the system on a certain time interval, and we would choose steady state if we wanted to learn more about the behavior of the system in a run that goes forever or in the long run kind of situation. So most models could be used for terminating or steady-state analysis. So now, assume steady state is desired. If we want to learn more about the behavior of the system in a steady state, we need to be sure this is so because running an analysis using to understand the steady state situation is a lot harder than the analysis that we did for terminating simulations. And naturally, the simulation run lengths can be long. Also, there is opportunity for different internal computation order, and this can change numerical results. Also, it underscores the need for statistical analysis of output. So let's talk about warm-up and run length. Most models start empty and idle. And what we mean by empty is that there is no entities present at time zero. What we mean by idle is that all resources are idle or not working. Right? They're ready for work, but they're not occupied. They're not busy at time zero. So this is an important thing that we need to take into account, because in terminating simulation, this assumption is okay if realistic. But in a steady-state simulation, this can bias output for a while after starting up the simulation. And bias can go either way. So it's very important to remember that bias doesn't always go one direction. It can actually go either way. But more often, you would get a bias downward. So results are biased towards lower what actually should be. In queuing type models, right, this is attributed to the situation where the queues get congested and there's too many people in the system for some time, and so it will definitely get, it will show some difference between what we would have if there's no entities and all resources are idle, right? If you look at the situation where there are some entities and some resources are going, then, or some resources are busy, then it corresponds to more congested state. But again, it's very important to remember that it's not always that we're going to have the results that are biased low. It's just a more often, right, or typical case that the results are biased low. But it can go either way. We could actually get a bias where it estimates something higher than it actually should be. And again, depending on the models, parameters, and run lengths, bias can be very severe. And so talking again, right, in terms of what we can do to remedy this kind of problem, right, we could think in terms of how we can take care of this initiation bias. For example, right, better starting state, more typical of a steady state, right? That would be desirable for us. And this means, right, we would need to throw some entities around in the model. And that kind of situation can be difficult or inconvenient to model. It would make the modeling more difficult. And first of all, right, how do you know how many to throw and where, right? Because if you overdo it, that can also bias that as well, right? So this is what you're trying to estimate in the first place, so you really don't know of how many, right, of the entities to throw around, right? And especially at which places as well. And so, right, another type of remedies that we can use for initialization bias is make runs so long that bias is overwhelmed. However, there are some problems with this solution as well, because it might work if initial bias is weak or dissipates quickly. But if that's not the case and the initial bias is very strong or persists, then running it for very, very long still might not take care of the strong initial bias. So another solution for initialization bias is to let model warm up, still starting empty and idle. And this can actually be a good solution. So what we could do, right, because first of all, right, it's more realistic, and so we can use run setup replication parameters, and we can specify warm-up period. So it's very important to take into account again what type of time units we're selecting for the warm-up period, because it can, right, if we don't select it correctly, then it would not give the warm-up period correctly or present the warm-up period correctly in the model. And so this type of selecting of warm-up period, it basically clears all statistics at that point for summary report in any outputs type save data for statistic module of results across up replications. So if you do indicate in your setup and replication parameters a specific warm-up period, then Arena knows to just throw away the statistic collected during that time period and, you know, get started the collection after the warm-up period over. So again, right, warm-up and run length times is important, right? We want to know, you know, what type of run or warm-up time versus run length time we should select if we're doing steady-state replication. So most practical idea is to do some preliminary runs, right? So again, starting with 0 warm-up, right? Do some preliminary runs, plot the results, and understand, right, through the plots, look at this graphical representation of some important output statistics to understand what happens in the system, where this warm-up length should be, and how long of a run length we need to be able to get the good understanding of the statistics for the steady-state output analysis. So again, right, this when we do that kind of thing, right, we could also simply eyeball them, but we need to be very careful about variability, right? Because if you only run a single run, look at the plot of a single run, it could be misleading. And so we need to make sure that we make multiple replications and then superimpose plots so that this will give us a better understanding in terms of variability from replication to replication, right? Because what if this replication is kind of outlier, right? It could show a longer warm-up length, or the opposite. It could show you the shorter warm-up length. And so we really need to be careful, right, to make those multiple replications and then look at the plots for all those replications together to understand, right, the variability, to understand whether this warm-up thing really affecting the model or it doesn't affect the model, and where to select this warm-up period. So we also need to be careful to note some explosions. And that's right basically when the system gets more congested. So a possibility is different warm-up periods for different output processes, right? So we could actually study different type of statistics or different type of outputs, and then for those processes select different type of warm-ups. So if you have to look at multiple processes and multiple outputs, to be conservative, it makes sense to take the maximum of warm-ups, right? If you need to look at multiple outputs together and analyze them together, then to be conservative, it really makes sense to take a maximum of warm-up periods. And again, right, it's very important to keep in mind that you must specify a single warm-up period for the whole model, because right, that's the only way you can do that, right? When you go to the run setup project parameters, you don't have multiple things there. You only have a single warm-up period or a place for a single warm-up period to be specified. So again, right, we can create, to illustrate what I'm talking about, we can create a single overall output performance measure for model 7.1. So we're gonna go ahead and change this model 7.1 and modify it into model 7.2. And we will also measure this time average total number of parts in the system. And so what it helps us to understand is how many parts in the system we have on average in time. And we'll use a statistic module, and because it's time average, it's a time persistent type of statistic, and so we'll label it as a total WIP, or work in process, and then use expression builder to build this time persistent statistic. And so we'll use this type of expression, so you can see, because we have 3 different type of parts in our model 7.1, which we will now change into model 7.2. We will need to add those entities of work in process for all 3 different type of parts. And very importantly, right, we also need to specify a data file for this output. So we'll have this output file named total work in process, or WIP, abbreviated history.dat, and this will save within run data. And so this is very important, because later you'll want to be able to plot these data. If we just look at it, right, and created the animated plots, like we know how to do that, after each replication, the plots clears it out. So it doesn't allow us to superimpose the plots for different replications. So we can't just do the animated plots. Instead, we'll have to plot these data using the output analyzer. So let me go ahead and get started and demonstrate to you how to do this. So here in Arena, I have my model 7.1 open. And now I can either click here to save the model, or click File, Save, As, and then rename this to 7.2. So I'm going to go ahead and rename this into 7.2. And so now the next thing, as I said, right, what we want to do is we want to plot these statistics in the output analyzer. So we're going to introduce the statistic for the work in process. So here again, we need a time persistence statistic, because it's a time average work, number of entities floating around. And I'm going to call this total work in process. And then I'm gonna build the expression. So here I'm just clicking, I'm right-clicking on expression cell here, and then select build expression from the drop-down menu. And then in the expression builder, I'm gonna go to basic process variables. So again, I go to basic process variables, and under entity, right? So click on entity. There is number in process. So I'm gonna click on number in process. And then here, instead of entity 1, right, under entity type, I'm gonna click and select from the drop-down menu part 1. And then similarly, I click off, do plus, right, because we're adding all the number in process or work in process for all different type of parts that we have in the system. So again, right under basic process variables, entity, and then number in process, I click on this number in process. Let's try again. All right, so number in process, and then instead of part 1, I'm going to select part 2, and then click off and add. And then again, under basic process variables, entity, number in process, I can select part 3 here under entity type. And so now this is my expression, right? So I'm adding the work in process for different entities where we have different entity types, part 1, part 2, and part 3. So it takes care of all different parts. And this is my expression. And right now, this is going to be the entire replication in terms of my data collection period, because I want to plot this. And then my report label, of course, is a total work in process. And I need to select here the output file. So I'm going to select an output file. And let me name this file total WIP history.dat. And this is going to be my output file. And so now it's gonna, now that I did that, I'm gonna save my model, and I can run this model to collect the statistics into the file. So to run it, I want to select under run control, right, go to batch run. So again, run control, and then make sure that the batch run is selected, which says it says no animation, right? So batch run makes it really fast, so we can run it through. So I don't really want to see the results yet, right? So I'm gonna click no, and I finish my run. So now I should have this total work in process history.dat in my folder. So as you see, we have modified the model 7.1 into 7.2. To speed up the run, we selected no animation, right? So we went to run control batch run. And we haven't unchecked the boxes, so we can uncheck the boxes and run setup and project parameters. So that would also speed up the run because no statistics will be collected. And we want to lengthen replication to 5 days and do 10 replications. So that's the part that we haven't done yet. So let's do that and then rerun again. So let's go ahead and do that. So we're back here in Arena. So as you remember, when I finished my run, I also clicked here to finish the run and stop the run. So now I can change my model. If this is still dark black instead of grayed out, then you need to click on it to stop the run. And then the next thing to do is to go back to run setup. To speed up, we can uncheck uncheck the project parameter parts in terms of statistics if you're not interested in some of the statistic collection and only need a certain one. Let me change this as well to 7.2. And we're going to change the in the replication parameters, we're going to change the replication length and also change the number of replications. So let's go ahead and do that. So here we're going to do replication length is going to be 5 days instead of 32 hours. And we did that because we want to study the long-run behavior of the system, because we're doing the steady-state analysis, so it's much longer than what we had before. Was 32 hours was just an hour, a day and a half, and now we increase the replication length to 5 days. And we're still not going to have a warm-up period just yet, but we need to change the number of replications to 10. So now we can say OK, and it's important that we keep this initialization of statistics in the system between the replication. Otherwise, we're going to have data that are correlated and not independent, and this helps ensure that we'll get independent data between the replications, which is exactly what we need for the statistical analysis to figure out the length of the run as well, and to better understand variability. So now that we changed number of replications from 1 to 10 and the replication length from 32 hours to 5 days, we're set. So again, I'm going to rerun this, and that will rewrite things into my file and clear off this file and rewrite the stuff. So again, make sure that you have the run control batch run here. And now that we got this done, let's run it again to get the new file. So I'm not interested in the results. Instead, I just want to plot my data. So recall that we're gonna do plotting data in Output Analyzer, and to start the Output Analyzer, we started from the from outside the arena, right? So we can go here and just start Output Analyzer, right? So I can just type in Output Analyzer and find my Output Analyzer under Programs. So I can click here on the Output Analyzer and it will get started. So you can see I just started Output Analyzer. So the next thing is I'm gonna create a new file in the Output Analyzer, and then I can add the files to it. So I'm gonna click on it to add the file, and instead of looking at those other ones, right, we're gonna use the total work in process history.dat. So let me add it there. And then the next thing I'm going to do is I want to plot my replications. So now I actually could do it 2 different ways. I could either click on Graph and then click on Plot and get here, or alternatively, I could click on Plot here, right, and then again this gives me the same, or brings the same dialog to me. So again, either Graph and then Plot, and that brings this dialog, or I can click on this button which also plots, right? So I get this dialog, and then the next thing I want to do is to add data files. So here, right, I can scroll down to the total work in process history.dat. I can select this, or I can browse for another file. So because I already added this file, right, it should be visible here as a data file that I want to plot. So I select this, and then in terms of the replications, if I just say replications 1, it will only plot the data from replication 1. Then I can say OK, right? And you can see this plotted the replication 1 data. If I click and change this, right, I can do edit, and instead say replication 2, it's gonna plot replication 2 for me. But I don't really want separately look at replication 1 or 2. I want to plot all of the data together, right? Because those superimposed plots is what will tell me the information, right? So instead, I will say add, right? Select this file, and instead of any specific replication 1, 2, 3, 4, 5, 6, 7, 8, or 10, I'm gonna choose all. So remember, this is different from what we did before, right? Where, you know, sometimes we might want to look at the lump data. Here in this case, we actually look, right, because if you remember in one of the previous lectures, when we did the statistical analysis of output for terminating replications, we actually got replication data for each replication. We had one value, and so there we selected lumped to analyze the statistics, right? Not for plotting purposes, but to analyze the statistics. Here, we're selecting all replications, and what it will do is we'll separately plot all of the replications. So I'm gonna say OK, and then you'll see how we'll get these superimposed plots. So now you can see, right, not only we see the total work in process 1, right, we also see the total work in process 2 as a green, right, this one in 1 is red. And all of them are superimposed together, right? And by superimposed, what I mean is that they presented on the same plot, right? Together, right? So the time that we had, those 5 days, right? It all corresponds to each of the plot, right? So now for each of the plot, we have a value for each of the time. And so it kind of tells us, right, you can see that at the beginning here, right there, we keep things, some of the stuff is still down until later where we have more variability, right? And you can see that, right, it's not, we could be more conservative, but at least we have up to this point where we would need to, right, consider that most of the with the exception of the green plot, right, the dark green plot, which is probably total work in process 9, right, we actually don't, right, we have most of them down compared to where this would be later on, right, and we also observe more variability later on. So some of it we attribute to the bias, right, there's very clear bias at the beginning too, where there's not much variability as you can see, right? Then later, this is still not, the system has not warmed up, right? Because we don't see some of those extra, you know, high values that we'll see later on. And so it's probably, and here it's only a single process that we have. So just to be conservative, we probably can cut it off somewhere around here, right? Where we start seeing more of variability for all of the different processes, right, or all different replications, not processes, but replications. So for all different replications, we have differences in terms of what's happening, and there's actually some of the higher as well as the lower values that we observe. While here at the beginning, we see more of the lower, so that tells us about this low bias, right? So if we included that, this part would bring down our statistics and we would talk about the lower, right? But again, as I said, the direction of the bias could be both ways, right? But in this case, conservatively, we could probably have the Warmup last up to this point here in time. So let's go ahead and review this. So what we did in the output analyzer is we first selected a new data group, right, which created this new data group. Then we added our file that we obtained by running the model. We got this total work in process history dat, which collected our statistics on the entities work in process for different type of parts. And then we were able to graph all replications, right, the plots for all replications together. And this we wouldn't be able to do just through using the animation. So we did graph and then plot, or alternatively, right, we clicked this button, and then, right, we added the total work in process dat to the plot, and we selected replication alls, right, all. We could also modify the title and axis labels, and this is what we got, right, a similar kind of picture, right, where at first you see, right, there's not much variability and also not much in terms of reaching some of those higher values for the work in process, right, or a number of entities in process. And so for some time, right, we don't see this. This is still a warm-up time. And so, right, again, there is no apparent explosion, but there is also some type of warm-up time that we can observe. And so we could estimate somewhere around 2,000 minutes is where we had our warm-up, so around about 2 days, right? The 2 days is actually 2,880 minutes. So next, let's talk about truncated replications. So when we talk about truncated replications, it's actually, what it means is how to move from this steady state, right? How can we use these truncated replications to actually study the steady state? And it allows us to, instead of using the, instead of trying to modify the steady state in some kind of way, we just need to identify the appropriate warm-up and the run length time, and then just make replications the same way as we did for terminating replications. Because in this case, knowing the appropriate warm-up time, we can select it in the model, and then the arena will clear off all the statistics for the warm-up, and then if we know the run length that is long enough, that will take care of all different variability issues in that length of time, then we can just study this model just like we did for the terminating simulations. And the only difference, as I mentioned before, is we need to specify the warm-up period. Before, when we did the terminating simulations, we typically just assumed the 0 warm-up period. And now, right, instead of assuming 0 warm-up period, we specify in a specific time there. So we would go run, setup, and then replication parameters. And then if we identify, for example, like we just did, a time of about 28,080 minutes or so, then we would, or 2 days, right, then we would just specify that type of time as our warm-up period time. So remember, we ran the system for 5 days, and then we determined that the warm-up was 2 days. So during those 2 days, right, the arena would discard all of the statistics collected during those 2 days, and then restart as new the collection of statistics during the remaining 3 days. And those 3 days would then, right, if we leave the run time the same way as it was as 5 days, so we'll only get the statistics for the run for that length of 3 days. And then if we did that, right, then we would get the data, and then we can continue the same way as we typically do for terminating simulations. We could continue with building the confidence intervals, doing comparisons, all type of statistical analysis, just as we did in the terminating state. So we could use this idea of truncating replications. So let's go ahead and create this model 7.3. We're going to modify model 7.2, and we're going to identify the warm-up period, as I said, to 2 days, equal to 2 days. And then we stick with a total replication length of 5 days, just like I mentioned. And we will stick with 10 replications that we did in model 7.2. And then we don't need the output file anymore because we're not gonna, so we're just gonna clear off the output file in the statistic module. And so these are the changes that we're gonna do. So let's go ahead and implement these changes in Arena. So here in Arena, I have my model 7.2. I'm gonna save it as model 7.3. So now it's gonna be model 7.3. And then, as I mentioned, we don't need the output file anymore, so I'm just going to clear this off. And so we got that out of the way. And the next thing is I'm going to go to Run, then Set Up, and then I'm going to change, right? So the only change that I'm making is a change to warm-up period, right? Before we had 10 replications, we're keeping that, and we're keeping replication length as 5 days. And here's the warm-up is going to be 2. And very important to remember, as I mentioned earlier in the lecture, important to remember to change time units. So this time unit, these are time units representing the warm-up period, right, or corresponding to warm-up period. So I'm going to change it from hours to days. And so now our warm-up period is 2 days. And so we're good here. So I say OK. And again, if we wanted to collect the statistics, we can go back and select the entity statistics or resource statistics as we want it, and then say OK. And I'll also change this to be model 7.3. And so we also have so we'll have the small manufacturer system with warm-up. And so now this is fine. We did the changes to replication parameters, which was important, right, to introduce this warm-up period of 2 days. So if we run this model, we can see the reports, right? So let's go ahead and run it. So again, as before, I already selected in run control, I selected batch run. So that's gonna keep things fast for me. So I'm gonna click on go. And now I actually will wanna see the results, right? So it says Arena simulation has run to completion. Would you like to see the results? So I'm gonna click yes. And this will open a report for me. So even if you said no, I can still open it through the report, right? And then here where I can see the category overview, so I can click here on the model, and under user specified and under time persistent, I can see my work in process, total work in process. So you can see this is my average work in process, and here's a half width because we had several replications, so we had about 10 replications, right? So not about exactly 10 replications. So this gives us a confidence interval, right? So we just use the average, and then we have plus minus the half width, and that gives us a confidence interval. So again, right, this is very useful. So let's go ahead and review. So what we got is we get this cross replications, 95% confidence interval, half widths in reports, and for total average total work in process, we got 15.89 plus minus 1.57, and that's what we saw. I'll show you. That's what we saw here, right? In the category overview for our model 7.3, we had 15.889, right? If you approximate it, that's 15.89, and then our half width is 157. And then here, when we did this without the warm-up length, this actually was 14.31 plus minus 1.38. And let me show you how we can see that. So here's my model 7.2. Now I switch to model 7.2, and under category overview, and then was user specified time persistent statistics total work in process, we get 14.3063, right, which approximates to 14.31, and then half width is 138. So that's exactly what we have. And so notice this difference, right, that we get compared to using the warm-up, right? So this in blue is our model 7.3 where we had the warm-up, and without warm-up we have this. So notice the average, right, is higher, and that basically tells us, right, that we have a bias. Without the warm-up we have a bias towards the lower average total work in process. And notice the difference in terms of the half width, right? And think about why do we have this difference in terms of half width, where the half width for the simulation with warm-up is actually larger. This is a difficult question, right? Because if you really think about it, what we did is when we using warm-up, we discarding some of those 5 days, right? So without the warm-up, we had 5 days length, and we counted all of the data towards the statistics, right? All 5 days were used to compute the statistics. So we had 5 days worth of data for statistics, but when we discarded 2 days in the warm-up, right, and put 2 days in the warm-up with the overall length of our replication still remaining 5, that means that we only collecting 3 days, right? 5 minus 2, 3 days of data. And so less data means that the confidence interval is going to be larger. And so that's exactly what we see here, right? And if we wanted to sharpen the comparison effect of a warm-up, we can run 100 replications with and without it, and again we'll get this with a warm-up, and we can get this without the warm-up. And so again you can see the same thing where there's a bias, right? The bias without the warm-up, where it lowers what we get with the warm-up, and in terms of the average total work in process. And again, right, the half width with the warm-up is longer because we're just not collecting as many days, right? So the half width with the warm-up are larger since each replication is based on the last 3 days and not all 5 days that we had without the warm-up. And so now when you think about the truncated replications, right, this problem of a smaller confidence interval, right, how can we take care of this problem, right? We have a choice. We can either do more replications with the same replication length, or the same number of replications but lengthen each replication. Either way, it means that we're running simulation longer, right? And so the second one, where we have the same number of replications but each one is longer, might be safer choice to guard against initiation bias. So I recommend using the same number of replications but increasing the replication length. For example, we could have increased, right, so instead of 5 days, because we discarded the first 2 days, we could run it for 7 days. And then we would still be then collecting it, right, but then it gives us additional, right, we're wasting some of the time, simulation time of course, but that improves, gives us smaller confidence intervals and improves the precision. So again, let's talk now about batching in a single run, right? So it's possible that some model may warm up very slowly. And so if we did truncation replications and discarding all the data, right, if the warm-up is very slow, we would have to discard all the data over and over again, right? That would mean that we might have to run simulations very long, right? So this can be costly, especially for some complex model. And so we would have to pay this warm-up on each replication, right? If we have 10 replications, we would have to discard this warm-up time every replication. So the alternative to that is to do just one really long run, right? So that we only pay this replication price or computational cost for replication only once, and then batch the single run. Of course, there is a trade-off, right? When we do separate replication, discard those, right? The data will be independent, but when we batch, right, they're not going to be completely independent. So again, right, the advantage is that we only have to pay the warm-up costs, computational cost to discard the warm-up data only once, right? And the problem is that we have only one replication, so you need more than that to form a variance estimate. So the basic quantity needed for statistical analysis, right, we can't just say, well, now we'll just use a single run, because that doesn't give us the information, right? Then we need to split up the single run into separate pieces. So a big no-no is use individual points with a single run as the data for variance estimate. Usually they're correlated, right, and the variance estimate is then biased, right, because you get this correlated, not independent measurements. So we can break each output record from the single run into few large batches. And the key point here is large, so that we don't really just look at single values, but we batch those, have those long or large batches, and then the data somewhere in one batch is going to be not so closely dependent on the data further for other batches. And so you will tally discrete time outputs, right, that are observation based. For time persistent continuous time, they're time based. And so we can take averages over batches as basic statistics for estimation, and that will give us batch means. So for tally outputs, we'll get simple arithmetic averages, and for time persistent, we'll get continuous time averages. And then we treat the batch means as independent identically distributed, even though they're not completely independent identically distributed. But if our batches are large, then the data somewhere in one batch, dependent on all the data from the other batch, are not going to be dependent, right? So again, the key is the batch size, keeping the batch size big enough so that this correlation between the successive batches is low. And you can read more about this in the ARENA textbook that explains, right, why you get this lower correlation compared to just looking at the single values. Still might want to truncate, right, but it's only once, right, and it's time-based. And so we only discard this warm-up only once. So when we do the batching in single run, what we're going to do is we're going to modify the model 7.3 into model 7.4. And so we're only going to have a single replication of 50 days, right? So if you look at this, it's pretty much the same in terms of the computational cost as 10 replications of 5 days. And we will have a single 2-day warm-up period. So before, when we had 10 replications, we discarded 20 days worth of data out of those 50 days. Now, if we're discarding only 2 days, we'll get 48 days that we will still keep. And in the statistic module, we're going to save WIP or work in process data once again for plot. and then we'll be able to do the plotting. So let's go ahead and do that. So here I'm back in Arena, and my model 7.3 is in the run mode. So what do I need to do? Of course, I need to click here on stop to stop the run mode. And then after that, right, I can save this 7.3, and then the next thing I'm gonna do is save it as a new model 7.4. So now I'm saving it as model 7.4, and here I want to do the changes to make it into a single run. So instead of 10 replications, I'm gonna have 1. So change here under run setup. In the replication parameters tab, under number of replications, it was 10. I just changed it to 1. And then still keep my warm-up period, but the replication length will be increased to 50. So it's going to be a single run of 50 days, right? Which is approximately the same amount, right, in terms of the computational cost for simulation as having 10 replications of replication length 5 days. So now that I've made those changes to number of replications and replication lengths, under replication parameters tab, I also going to change this in project parameters from 7.3 to 7.4. So now, okay to that, and I also want to record the data into the output file. So in the statistics module, right, so under advanced process we have our statistic, and this is where we had our total work in process. So I'm gonna save the output data again, but under a slightly different name. So I'm gonna name it total work in process. Single run.dat, and then I'm gonna save this model and run it. So again, make sure that in the under run control that we have batch run selected, as we do have it selected. And so next, after I run it, it will create this .dat for me. Right, so again, I don't want to overwrite my file from the previous model 7.2, so I named it a little differently, slightly differently. So I'm going to run it, and I don't really want to see the results just yet. Instead, I'm going to stop this run for now, and I'm going to go ahead and plot my data in the output analyzer. So again, I could either click and start the output analyzer, or here I already have output analyzer selected. So let me just go ahead and save this for now. So this is going to be my model 7.2 data group. Output. And I can have a new data group files. And here, this is where I'm going to add this total work in process single run.dat, and again I can plot it. So this is where I could click on plot, or I can batch or truncate things, right? So if I just plot it, I would get this, right, which is my single data. So you can see, right, it gives me the single data and all saved in this. But I can also do the analysis. For example, I can choose this batch truncate and then choose my data file for total work in process single run data group. And then here I only have a single replication, so I can just leave it as one, or I can do either all lump. It doesn't really matter in this case because it's a single run. And so then, right, I can also select the truncation either by duration or time. So typically by time, so I could truncate it at my 2 days, which is approximately 2,880 minutes. And then here again by time, I can choose the the size of the batches, and then select the type of batches that I get, right? So again, here might be some really larger size because we want our batches to be large. So to keep it large, say if I wanted to batch them in the sizes of approximately 5 days, then in terms of the time in minutes, that would be 7,200. So then I could also, save the batch means in the file if I wanted to. If not, it just will produce a summary for me, to tell me how many batches produced and the covariance between batches, right? So if I selected the way I did, right, I selected this initial truncation time, then I have this number of batches that I got, right? If selecting this time, right, notice, so the time that I selected was 5 days, which is 7,200 minutes. So that produced 9 batches for me. And there is also some trailing time that got truncated that wasn't used. So I could have possibly selected a smaller number. And so you can see that estimate of variance between batches, right, is this, right? So it's a negative 0.1. So just to demonstrate, let me batch it in a different way. So I can click here, and let's say I'm gonna make the batch size much smaller, so only 2, or actually, right, let's say 300 minutes, right? So if I did this 300 minutes, I'll get more batches, but notice the covariance, right? So I got a whole bunch of batches. I got 230 batches compared to initially what I had is 9, right? And so now these batches are significantly smaller in terms of size, right, than my previous batches. But notice how much my covariance increased, right? So they're very heavily correlated because the covariance is 0.9 versus not much of a correlation was 0.1, right? So this is very weak correlation compared to this very strong correlation when my batch size is too small. So the lesson is, be careful what you select as your batch size, right? Make sure your batch size is small, is large enough, so you actually get a small covariance between the batches. So now let's return to the lecture, and this is where we have this work in process plot, right? So this is for just a single run, right? So when we batch a single run, if we batch it, how to choose a batch size, right? So I showed you, right, what we can do is we can look in terms of the batch size and what type of covariance it gives us, right? Equivalently, how to choose a number of batches for a fixed run length. And we also want the batches to be big enough so that batch means appear uncorrelated, right? Or the correlation is very weak. So ARENA attempts to form 95% batch means confidence intervals on steady-state output measures from within the single replication. And a half-width column and reports from one replication. In category overview report, if you just have one replication. In the category by replication report, if you have multiple replications. And it uses internal rules for batch sizes, right? So you can actually see more information, more details about it in the ARENA textbook. And ARENA also wants to form 95% batch means confidence intervals and steady-state output measures from within the single replication. So it won't report anything if your run is not long enough. And it may tell you insufficient, right? You might see there in your report insufficient if you don't have the minimum amount of data that ARENA requires even to form a confidence interval. And also you might see correlated, and the word correlated appears on the report in ARENA if you don't have enough data to form nearly uncorrelated batch means required to be valid. So if you're doing a terminating simulation, you should be doing multiple replication, in which case ARENA reports cross-replication half-width and not batch means half-width. So now if we look at the results from Model 7.4, in the category overview report, our average total work in process is 13.64 plus minus 0.38. And the half-width is considerably smaller than for truncated replications. 10 replications, 5 days, each day 2-day warm-ups. So you can see that here we spend only a total of 2 days warming up, and with truncated replications we spend 10 times 2, 20 days warming up. And so we can check batch means half-width during the run. For example, ARENA has variables t half tally ID and d half dstat ID, and we can use it to use a condition, right, to check the batch means half during the run and stop the run, after we reach a certain condition. So we can decide on your own batch sizes. You can form batch means and confidence interval by hand using output analyzer, just like I showed you. And question is why, right? Because you can use it in the statistical comparison procedures, and you can read more details about it and find more details about it in the ARENA textbook. So again, what to do, right? There are several approaches or methods for steady-state statistical analysis, and I demonstrated to you the truncated replications and the batching of the single run. But there are many more that exist. And so the opinion is, right, you can avoid steady-state simulation if your goal of the project, right, depending on the goal of the project. Or if you really need to do it, right, if your goal of the project tells you that you need to understand the steady state or long-term behavior of the system, and you really want to do the steady state, then first you want to try warm-up and try truncated replications. And if the model warms up too slowly, then making truncated replication is inefficient, then you should consider ARENA's batch means method in a single long run with a single warm-up period at its beginning. But, right, you can't really use these statistical methods in Process Analyzer or OptQuest. Right, you can only use it in Output Analyzer. So other methods, right, it depends on the goals, right, in the steady-state statistical analysis. So you can see more reference in the text in terms of what other methods are there. So again, thanks. This is going to be very useful for you, and I hope that you learn a lot from this lecture.